We are in the home stretch with triple integrals. We're going to look at what are known as cylindrical and spherical coordinates as two methods to help us evaluate triple integrals where rectangular coordinates result in integrals that are just very complicated to evaluate. So stay tuned as we look at cylindrical coordinates first and then move into spherical coordinates later. Just as we had polar coordinates to deal with complicated regions for double integrals, we can use an analog for polar coordinates for three-dimensional regions that we are evaluating triple integrals over. The analogs are, there are actually two of them. We have cylindrical coordinates and spherical coordinates. Spherical coordinates are quite a bit more complicated, so we're going to leave those till the end. Cylindrical coordinates, however, are a really nice generalization of polar coordinates. So suppose that I'm wanting to find the coordinates of a point x, y, z in three-dimensional space. So we know that this point is located based on its location with respect to the y-axis, its location with respect to the x-axis, so trying to get this nice and aligned here, and its location on the z-axis. So we have our x, we have our y, but we know that we can take, instead of viewing this point as xy in the xy plane, we could view it in terms of these polar coordinates. So instead of having x comma y, we could represent it in terms of r and theta. Here I can have that my length here is r, and I can have that my angle from the x-axis to the y-axis is theta. So this is going to give me that my x here, using a little bit of trigonometry, my x value here is going to be equal to my r cos of theta. And similarly, I'm going to have that if I look at the other edge over here, that my y is going to be equal to r sine of theta. So this allows us to take a point in three-dimensional space and represent it partially in terms of polar coordinates. So in total, what we end up with is that our x is going to be equal to r cos of theta. Our y is equal to r sine of theta. So here, these are our polar coordinates. And finally, we're going to end up with just z equal to z. We're not representing z in any different way. It's still going to be rectangular. So here we can see that this is essentially polar with a z component. And that z component is being represented in the standard rectangular way. Now that we have cylindrical coordinates, the question is, how do we translate this into a triple integral? So what we're wanting to work with is we're considering, okay, we've got a triple integral over some region in three-dimensional space, E, and we're dealing with our multivariable function f of x, y, z, and we're evaluating with dv. In the previous week, we utilized dv as dx, dy, dz, or some combination of in different orders, depending on our order of integration. Now we're wanting to switch this so that we have, instead of those little rectangular boxes making up our dv, the boxes are going to have a slightly different shape because of the way that we're setting up the integral. So what ends up happening here is we've got a situation where if we looked at what was happening in the xy plane, when we were setting up our double integrals, we had that this little region here that I'm highlighting in yellow, or I guess green, this region was what we called dA. And our dA was going to be equal to r dr d theta. If you need a reminder of where this came from, I encourage you to look back at the videos when we were working on polar coordinates. So now that we have our dA in the xy plane, we need to give this some kind of dimension. And we're going to give it that dimension by giving it a little bit of a dz and a height, thus giving us a volume. So here we can imagine lifting up these pieces so that then what I'm ending up with is a little volume that looks something like this. And this is the little volume here where I have this as my dz. This entire volume, now that I'm going to color in yellow, this volume is going to be my dv. So in total, we have that our d sub v. So this is dv, which in total seems to be equal to dA times this dz. And we know that our dA is going to be our dr d theta, and then we're multiplying by our height dz. This means that we can translate our original integral in terms of these tiny box volumes. Rather than tiny box volumes, they're like little curved box volumes. And so our original integral can be rewritten as, we'll have a triple integral over our region E. We're still dealing with our multivariable function, f of x, y, z, but we want to translate now our x and our y in terms of our polar coordinates. So in total then, we're going to have that our x is going to be r cos theta. We're going to get r sine theta for our y. We'll have z for z. We're not changing that, but we are going to have to multiply by r dr d theta, and then finally dz. This order can change depending on which order of integration you want to use. We could do d theta first, but normally integrating in the standard way in our polar coordinates for this first bit is definitely the way that we want to go. So generally, it is helpful to integrate with respect to z first. We're going to see how that works in a couple of slides coming forward. Here's our first example of using cylindrical coordinates to evaluate and set up a triple integral. Yes, you could set this up in terms of rectangular coordinates, but you're going to end up with an integral that's a whole lot more complicated to evaluate. And so setting it up with cylindrical is definitely going to be the way to go here. Okay, so to start things off, we need to go ahead and make a rough sketch of what we're doing. So we know that we are working with in the first octant, so here where all of our variables x, y, and z are going to be positive. So here I have my z, I've got my y, and I have my x. We're looking at the region underneath of this paraboloid, which has a vertex at z equal to 1, and then is going to be moving downward. So in total, if we want to plot what this looks like, we're working in the first octant. So really, we only care about what is happening over here. And we can imagine having some kind of dimension to this. So trying my best to give this guy a little bit of dimension so you can see what this surface looks like. So this is our region E. It's the paraboloid, and we are restricting to this first octant. Now we need to figure out where we are entering and exiting E. And here is why focusing on Z first makes, as our first limit of integration, is always going to be a little bit easier. Here we can see that we're looking only in the first octant, and so we're actually going to only be looking at when our z values are going to be bigger than 0. And so if we're entering and exiting through this surface, we're going to have things that look something like this. So I enter and I exit. If I'm over here, I'm entering and then I am exiting up through the top, and so forth. Here I can enter, and then I can exit. So from this, we can see that every single time that we enter through this surface, it's always going to be when my z is equal to 0. And every time that I exit, it's always going to be happening through the paraboloid. So it's always going to happen when my z is going to be equal to 1 minus x squared minus y squared. Now here's where we need to pause. We are wanting to eventually switch this into cylindrical coordinates. So at some point, we're going to want to make sure that these x's and y's don't have anything to do with our integral. Everything should be in terms of r and theta. At this point, the steps that we're following are exactly the same steps that we followed when we were doing triple integrals in rectangular coordinates. Now that we have our rough sketch of the region, we want to project that region down. And so in this case, we're going to be projecting down onto z equal to 0. And what we'll end up with is a picture that looks something like this. So we have our y-axis, I can make that straight. We have our x-axis. So here's my y, my x, and my region is going to look something like this. So I have that it is going to be the quarter circle. I can, there. And I'm going to highlight that in yellow to match our image on the other side. Okay, so in this case, we know that any time that we're trying to evaluate a double integral over a circular region, working with our polar coordinates is usually the way that we want to go. And the same thing can be true here. So we have that if we look at our bars and how things are changing, we're looking at changes like this. So our theta is ranging, and we also have that our r is ranging. So first of all, we can note that this is happening when z is equal to 0, and we have that z is going to be equal to 1 minus x squared minus y squared. So to find the equation of this boundary, we need to set these equal to each other. So that's going to mean that 0 is going to be equal to 1 minus x squared minus y squared, which means that we're really just working over the unit disk. And we know that this is true when our r is ranging between 0 and 1, and our theta is going to be ranging between 0 and 2 pi. Because we now have things in terms of r and theta, we want to change our entering and exiting to be in terms of r and theta as well. We can rewrite this as 1 minus r squared, because x squared is going to be r cos theta and y squared is going to be r squared sine squared theta. Now that we have all of the information, we can set up our iterated integral in cylindrical coordinates. We have the triple integral over e of x and then dv is going to be equal to. So we have our triple integral, we're going to have limits on this. We know that we're going to have our x, since we're working in cylindrical coordinates, is going to change to be r cos of theta. And then we're going to need to account for our dv being r, and we're first of all doing z first. So it'll be dz, and then we'll have dr, and then we'll have d theta. So in total, we'll have our entering and exiting for z. Here we know that we're going to enter when our z is equal to 0, and we're going to exit when z is equal to 1 minus r squared. Our values for r are going to be ranging between 0 and 1. So we'll have 0 and 1 for our limits of integration here. And then finally, we'll have 0 to 2 pi for our limits of integration for theta. This gives us in total a nice triple iterated integral in terms of r, theta, and z, where we have that it will be r squared cos of theta integrating with respect to z, then r, and then theta. Before we move on to a few more examples with cylindrical coordinates, I want to make a few remarks. Again, cylindrical coordinates are going to be particularly useful when our region is symmetric about the z-axis. However, if it's symmetric about a different axis, we can adjust. And the way that we do that is basically taking our plane to be in polar coordinates. So when we were symmetric to the z-axis, we had that the xy plane was in polar. But if we had that our region happened to be symmetric about the x-axis, in this case, what we're doing is we're going to have the x-axis be where we're taking our entrance and exit. And then here we have that the y-z plane is in polar. If we were symmetric about the y-axis, we could take the zx plane in polar coordinates. Again, when we're dealing with cylindrical coordinates, taking your first variable of integration as the variable you're symmetric over is generally the good idea. So here you want to choose your symmetry axis first. For the most part, for examples that we'll see, this tends to be the z-axis. And again, here, symmetric about a different axis, you're going to want to integrate with respect to that variable first. The setup will be exactly the same, it's just setting up an alternative coordinate plane in terms of polar coordinates. In this example, we are once again going to use cylindrical coordinates to set up an integral that we would normally set up using rectangular coordinates. Here we're looking at a region lying inside of a cylinder of radius 4 and between two planes. So we're cutting off the cylinder so that it doesn't go on forever. We're going to cut it off at z equal to 4 at the top and z equal to -5 at the bottom. Okay, so the region that we're going to be looking at, so here I'm going to have, let's say, my z equal to 4, and our cylinder is going to look something like this. Okay. Again, this is happening at z equal to -5, and here this is at z equal to 4. And the region that we are considering is here. So filling this in with our little swirly lines to give it some kind of dimension. Okay, again, we need to figure out where we are going to be entering and exiting through this surface. So we're always going to be entering from the bottom to the top. So my entering and exiting is actually pretty nice here. So my lines, I'm parallel to the z-axis. So my entering and exiting is happening in that way. We can see that we are always going to be entering at z equal to -5. And similarly, we are going to always exit when our z value is going to be equal to 4. And now we need to do the projection. And that projection is going to happen when I look at where I am sitting in my xy plane. So here, this projection, put it over here, we have our x-axis, we have our y-axis, and the region that we are considering is going to be a circle, and in this case of radius 4. So we know that our cylinder has a radius of 4. We'll see why that circle is radius 4 in a moment. But here we have, again, our y-axis, our x-axis, and the region that we need is given here. So I'm going to highlight this one orange so that we can see it a little bit better in this image too. Okay, so what we end up having is that this is happening when our z is equal to 0 And we have that our x squared plus y squared equals 16. It doesn't change at all. This equation has nothing in terms of z. It's just going to be the circle x squared plus y squared equals 16 located within the xy plane rather than say at z equal to 4. So in this image, again, projecting it downward, we want to figure out how our theta is ranging and how our r is ranging. And in this instance, what we end up with is we have that our r values are going to be between 0 and 4, and our thetas are going to be between 0 and 2 pi. So if we want to set up our iterated integral, or triple integral originally here, x squared plus y squared and dv, we're going to need to set this up in terms of our polar coordinates for the xy plane. In doing that, we're going to have the square root of r squared, because x squared will be r squared cos squared theta, r squared sine squared theta. That'll just leave us with an r squared. And then we're going to integrate with respect to our polar coordinates. So we'll have our r, we'll have dz, dr, and d theta. We know that our z values are going to be ranging from where we enter at z equal to -5 to z equal to 4. And for our r, that's going to range from 0 to 4. And finally, for our thetas, that is going to range between 0 and 2 pi. Notice in this instance, we ended up with a integral where everything was constant. We have that our values here are all constants, and we're just going to be evaluating r squared dz dr d theta. Cylindrical coordinates, when my region was a cylinder, end up so that everything is just constant in terms of the limits of integration for this triple integral. Let's look at one more example of using cylindrical coordinates before we move to spherical coordinates. This example is going to be a little bit trickier to set up and visualize. We're wanting to set up a given triple integral as an iterated integral in cylindrical coordinates. And we have a region that is within a cylinder, above a paraboloid, and below a plane. So as always, first good idea is to go ahead and plot and sketch what this region is going to look like in our x, y, z plane. So from here, we have our cylinder. We know that our cylinder has a radius of 1. It's going to look something like this. And we're going to pull it down however far we need to in order to visualize. And we're also looking at the paraboloid, who has a vertex at the origin. And so that is going to look something like this. And note that I'm cutting off at the plane z equal to 3. So we don't need to consider what is happening above this value of z equal to 3. Now we're needing to have the region within the cylinder and above the paraboloid. I'm just going to give this paraboloid a little bit of extra dimension to visualize what is going on here. And to actually get the region we're looking for, again, it's going to be above the cylinder and inside the cylinder and above the paraboloid. So the region that we're looking for is this one. And again, we need to figure out where we are entering and exiting through this surface. Because we're symmetric to the z-axis, our entering and exiting is going to be parallel to the z-axis. We're always going to enter, I'm changing my color here, at the bottom of the paraboloid, and then we're going to come up through the paraboloid Same thing, entering at the bottom, coming out through the top, entering through the bottom, and coming out through top. Here we can see that we always enter our volume when our z is equal to x squared plus y squared. And we're always going to exit when our z is going to be equal to 3. We're cutting off at that point. That is where we're going to be exiting. Now we need to project our region E down onto the XY axis. And if we do that projection, what we're going to end up with is something that looks like this. So again, bear with me as we work through this. Projecting down, we're going to end up with a circle. We can do this algebraically as well. So we're going to project onto the XY plane. This is going to be happening when our z is equal to 0, and we have that x squared plus y squared is equal to 1. There we can see that we're going to end up with just the unit disk as the region we are integrating over, keeping our colors consistent here. We have our circle that we are looking at over the XY plane. So here we have our Y, and here we have our X. We have a nice radius of 1. And we can see that in this case, our R is going to be ranging between 0 and 1, whereas our theta is going to be ranging between 0 and 2 pi. Again, ending up having our change in R going from 0 to 1, and this is happening for all values of theta from 0 until 2 pi. Now that we have all of this, we can set up our iterated integral. So we have that the triple integral of E of dz, not dz, sorry, we have just z dv. Because we're working in cylindrical coordinates, we don't need to change this. If there were x's and y's, we would need to make a change. But here we can end up resetting it up as an iterated integral of z r dz dr d theta. Our z values are going to be changing from our bottom limit, which, note, was z equal to x squared plus y squared. However, if we want to throw this into polar coordinates, we're going to need to change z equal to x squared plus y squared to be in terms of r and theta, and this will be equivalent to r squared. So we're always going to have that we're ranging from r squared up until that exiting value of z being equal to 3. For our r values, they are going to be ranging between 0 and 1. So we'll have 0 to 1 here. And then for our theta values, they'll be ranging from 0 to 2 pi, giving us an iterated integral in terms of z, r, and theta. We're now moving on to the next way to represent points in three-dimensional space. We worked through cylindrical coordinates, which was where we had just one plane in terms of polar and then had another coordinate in the standard way. For spherical coordinates, this is truly the generalization of polar coordinates to three-dimensional space. In polar coordinates, we were viewing the xy plane instead of as a grid, viewing it as a bunch of concentric circles. Our location in the plane was dependent on which circle we were on and where we are on the circle. So we had our radius r to represent which circle, and we had the angle theta to represent where we were on the circle. When dealing with spherical coordinates, we're doing a very similar thing, except we're viewing the three-dimensional space as a bunch of concentric spheres. So rather than thinking of where we are within the grid of three-dimensional space, we want to ask ourselves, which sphere are we on and where are we on that sphere? If we can answer those questions, that's how we're going to set up our spherical coordinates. Now, bear with me, setting up these spherical coordinates is actually pretty complicated because when we were dealing with polar coordinates, we just had one angle to represent where we were on the circle. When dealing with spherical coordinates, we have two angles that are going to define where we are on the circle. Those angles are what are known as phi and theta. Notice I made a little bit of a typo that I switched. Here, our angle theta is going to have to be with respect to the x-axis, whereas our angle phi will be with respect to the z-axis. Let's go ahead and set this up. Bear with me, it's going to be a little bit complicated and it might get a little messy. So first of all, we're going to be working with a point, call it P of x, y, z. So we want to know, where is this point on a sphere? So the way that we can set that up is to think about the distance from the origin to this point, P of x, y, z. This is going to be my value rho. Rho is going to be the radius of the sphere that this point is on. Now that I have rho, we're going to have to set up a whole lot of other things to understand not only where we, which sphere we're on, but where we are on the sphere. I know that I'm going to be on a sphere of radius rho, and so if this is my length rho, then my sphere is going to be generated by taking all of the possibilities of moving this radius around. And so we can look at the angle from the z-axis to this point. I've got my rho, and then I can tilt from the z-axis, and that is going to be what I call my angle phi. From this phi, we can then end up seeing that we can create a right-angled triangle. So I'm going to have my right-angled triangle looking something like this. And I'm going to draw that because this is going to come in handy later. Trying to make this look as nice as I can. Okay, so this is a right-angled triangle. We have our right angle is happening here. And we're going to have a few new things that we can add in. We can realize that using a little bit of trigonometry, this is going to be the base of my triangle. And so in this case, we're going to have that this is going to be rho cos of phi. And we're going to have that our length up here is going to be rho sine of phi. We can then see that this distance down here is going to be, again, rho sine of phi. I'm essentially setting up a box. And then also just to keep as few lines in here as possible, because there are going to be a lot of lines, we're going to have that this distance as well is going to be rho cos of phi. So this is representing kind of where I am on the sphere relative to the z-axis. We now need to know where we are on the sphere relative to the x-axis. To find out where we are relative to the x-axis, we need to define a new angle, and that angle is going to be the angle here that we get from taking this line from the x-axis. So this angle here is going to be the angle that I call theta. Now that I have this angle theta, I can set up another triangle and do even more trigonometry here. So I'm going to end up with this as another triangle. And note that this is a right-angled triangle. And we can figure out what the sides of this triangle are, though it's going to take a little bit of extra handiwork to figure out what those are. Notice that the hypotenuse of this triangle is rho sine phi. So we can set up a little bit of trigonometry using rho sine phi as the hypotenuse. So here I have the base, here I have the height, and so I'll end up having that this distance here is going to be my hypotenuse, which is rho sine phi, times we're going to end up with sine of theta. And then on this side, because this is going to be the base, we're going to have that it's going to be rho sine of phi and then cos of theta. Now that we have this picture set up, we can figure out what our x, y, and z coordinates are in terms of rho, phi, and theta. We'll end up having that our x is going to be equal to, we'll have rho sine of phi times cos of theta. Again, we get that based on this part of the diagram. We have similarly that our y is going to be equal to rho sine of phi, sine of theta, and our z is going to be equal to rho cos of phi. We have this so that we can now set up a given triple integral in terms of spherical coordinates. Note that we have a few extra little arithmetic tricks under our sleeve now that we're in our spherical coordinates. We would have that x squared plus y squared plus z squared is going to be equal to rho squared. Our rho, because we're working on a circle, or on a sphere, is the radius. It's always going to have to be bigger than or equal to 0. This is a condition that we took when we were dealing with polar coordinates, making sure that our r was always going to be positive. We also have that our theta is going to be between 0 and 2 pi. And this one's a little bit harder to visualize, but our phi is always going to be between 0 and pi. So how does this work? So our theta is going to be all the way around. So that's why we're only going to have that our theta can be between 0 and 2 pi. We're taking where we are relative to the x-axis all the way around. Now, the angle phi is the angle from the z-axis to this line here. And so from this point, I only need to think about the angles from 0 to pi. I can get all of the other values based on where we are in the xy plane, and having, for example, if my theta was, say, 3 pi over 2, I could have that my rho was down here so that my phi would be between 0 and pi. There we go. When setting up these spherical coordinates, we're essentially going in the order of rho, phi, theta. I choose my rho. My rho is which sphere I'm on. I choose my phi, so I could have my phi is going to be a really steep angle. So that's the example I was attempting to describe in the picture there. So I go from a parallel to my z-axis, I take a really big angle close to pi, and then from there I can spin this around by 2 pi, and so in that case I'm ending up getting all of the possible points that give me my angle of phi, and then 2 pi as my option for my theta. Before we convert our triple integral into spherical coordinates, we need to identify what our tiny volume is. To set this up, we need to account for our change in rho, phi, and theta. Remember from the previous slide that I recommended when dealing with spherical coordinates, it's easiest to start with rho, then go to phi, and then go to theta. That's exactly what we're going to do here. We can highlight this distance here as my distance rho. And so then I would have that this distance here could be my little change in d rho. We also, now that we've dealt with rho, need to account for theta. So, or sorry, phi. We deal with rho and then phi and then theta. So this distance or this angle, this tiny change is what's going to be my d phi. And now that we have d phi, we need to kind of focus on the slice that's being made here. This slice looks really, really similar to what we were dealing with when we looked at polar coordinates. And we can make a similar argument and note that this length here is going to be equal to rho d b. We have the essentially the circumference of the circle, but only a small little part of it. The rho giving us the radius, and then d phi giving us the portion that we need to focus on. Okay, we've dealt with rho, we've dealt with phi. We now need to account for theta. And to do that, we're going to essentially project the analog of this slice down onto the XY plane. In order to do this, we're going to take all of these points on our tiny volume and bring them down into the XY plane. I'm going to have to do a little bit of erasing here, but it'll happen eventually. And we can imagine that this is a shadow down onto the XY plane. So what it's going to end up looking like is something like this. And I'm going to do some erasing here so that this is a little bit easier to see. Go. So these dotted lines representing that projection onto the XY plane of our tiny volume. So we have a new little slice down on the XY plane. The thickness of this slice has to do with our angle theta. We have that this angle here is going to be our d theta. And now that we have d theta, just like we had this length, we can ask ourselves what this length is. And this is going to take us back to the previous slide where we set up our spherical coordinates and noting if this is my rho and my line here is not the best, but we're going to end up with that our distance here is going to be equal to, we're going to get rho sine of phi as the length here. Again, returning back to this image where we have rho sine of phi as the length down on the XY plane. Now that we have that as rho sine of phi, we can figure out that the length here, just like we found the length here. This length is going to be equivalent to rho sine phi times d theta. And at this point, we're able to set up what our tiny volume is. Note that the distance here is exactly the same as the distance here. So we can mark these as the same, noting that that is going to be rho sine of phi d theta. So if what we're trying to set up is a triple integral of over a region E of f of x, y, z dv, we're recognizing that, okay, well, our dv, our tiny volume, is going to be equal to, we're going to have that d rho given by this distance here. We're going to have to multiply that d rho by rho phi to give it some height. So we're going to multiply by rho d phi to give it some height. And then we're also going to have to give it some width by taking this region and then rotating it to give me that volume. And I'm going to rotate it by that tiny angle theta, or just d theta. But The distance that I'm rotating is going to be rho sine phi d theta. So in total, we're going to have times a rho sine of phi and then d theta. And this makes a triple integral that will then be rewritten over the region E. And here's where things get a little bit complicated. So we're going to have to replace not only our dv with this expression, we're going to have to replace x, y, and z with their corresponding expressions in spherical coordinates. So that's going to be pretty. So we're going to get f of, we have that our x is going to be rho sine of phi cos of theta, rho sine of phi sine of theta, and then we're also going to have rho cos of phi dv, where our dv is going to be equal to this expression here. So where, and just to simplify this, dv is going to be equal to, we're going to have rho squared sine phi, and then d rho d phi d theta. That is how we're going to have to transition from rectangular to spherical coordinates. You're probably thinking, why would I want to do this? And maybe you'll see, but it's also pretty awful. So let's go ahead and apply spherical coordinates to an integral. In this case, we're setting up a triple integral over a region E defined as follows with respect to a cone, a sphere, and a plane of z equal to 0. The steps that we're going to follow are very, very similar to what we had done previously. We just need to take into account the fact that we're working in these spherical coordinates. First things first, let's make a sketch of the surface that we're working with and the volume that we're trying to set up limits of integration for. So we're first starting off with a sphere, and we know that this sphere has a radius of 1. And we're also working with a cone which is centered at the origin and facing up. So in this image, we have a rough idea of what our surface is looking like. We also know that we are restricting from z equal to 0 and up. So we're only going to be looking at where our sphere is above the z-axis. So I can actually erase a bit more here. Okay, so we're looking at the region, which is going to be below the cone and inside of the sphere. So to give this cone a little bit of depth, we are looking below the cone and inside of the sphere. We don't want the region inside of the cone. What we're actually looking for is going to be the region given here. So trying to highlight this to give it a little bit of depth so that we can see what we are working with. Now that we have our rough sketch of E, we need to convert the equations of the boundary surfaces into spherical coordinates. We have two boundary surfaces. We have z squared plus x squared plus y squared equals 1, but this translates directly to rho squared equal to 1 or just rho equal to 1. Remember that with our rho, it's only going to be bigger than 0. And so in this case, rho equal to 1 is the only solution that we need to choose. The second set of boundary equations is that we have z squared is going to be equal to x squared plus y squared. We can switch this into spherical coordinates by noting that our z is going to be, we'll get a rho squared, we'll have a cos squared of phi equal to, we'll have rho squared, sine squared phi cos squared theta plus rho squared sine squared phi, and then a sine squared of theta. Running out a little room. We get rho squared cos squared phi is going to be equal to, I can factor out a common factor of rho squared sine squared phi and be left over with cos squared theta plus sine squared theta. Here we know that cos squared theta plus sine squared theta is going to be equal to 1. So we're just left with cos squared phi equal to sine squared phi, which means that we have to have that tan of phi has to be equal to 1. This is only going to happen when our angle phi is equal to pi over 4, or it could be when we have 3 pi over 4. We can eliminate 3 pi over 4 because we know that our z variable has to be bigger than or equal to 0. So this leaves us with our phi being equal to pi over 4. The cone can be represented by just phi equal to pi over 4 in our spherical coordinates. We now want to set up this iterated integral. And again, we want to do rho, phi, and then theta. So we're first going to think about entering and exiting in terms of our rho. So if we think about moving in the positive rho direction, where we have that our angles are held constant, which surfaces do we enter and exit through E? That's going to take us a little bit of extra visualization here. So in order to figure this out, we're wanting to think about our rhos. So remember, rho are going to be these distances here. And it seems like if I draw out where I am entering, it's always going to enter through the origin, right through the center. And I'm going to exit out the edge of the sphere. I can keep my rho and my my theta and my phi constant and have a different entrance and exit here. Maybe it's here, and maybe it's here. In all of these instances, we can see that we are entering through our rho equal to 0. This is happening at the origin. And we're exiting when we have that our rho is just equal to 1. We're exiting always through the sphere. We now know that on moving back to this slide, we are going to enter through our rho equal to 0, and we're going to exit through our rho equal to 1. Now we need to work through the other variables. So here I was holding my rho and was changing. So rho is changing when I have that my phi and my theta are constant. We need to work with the other variables now. So say I want to think about my change in my phi. So phi is going to be the variable that gives me from my z-axis, my angle from the z-axis. And so my changes are going to look like this. So here I start and I leave, I start and I leave. It turned out kind of funky, so I start and I leave, I start and I leave, and so forth. In those instances, we have that our rho and our theta are being held constant. And we can see that if we think about where our phi is changing, it's always starting from the cone and then it's exiting through the bottom of the sphere. So we seem to be going from the cone to the xy plane. And that is going to happen where our cone here is always going to be according to what we know from converting into spherical coordinates, the cone is going to be phi equal to pi over 4. And the xy plane here is going to be, well, it's the angle down from the z-axis, and that's just going to be phi equal to pi over 2. So our phi is always going to range from pi over 4 to pi over 2. All of these entrances and exits for our angle phi. Lastly, we need to figure out what is happening with our angle theta. And remember that theta is going to be the angle from the x-axis. And in this case, we can see that we're taking all of these arches and reaches and radii out for all different values of theta. Our theta is ranging all the way around so that our theta goes from 0 to 2 pi. This gives us all of the possible values for our limits of integration to help set up our iterated triple integral in spherical coordinates. To remind ourselves of this setup, for rho, we were entering through rho equal to 0 and exiting with rho equal to 1. For our angle phi, we were entering when our phi was going to be equal to pi over 4 through the cone, and we were going to exit when our phi was going to be equal to pi over 2, the xy plane. Finally, we needed to think about our theta, but theta was pretty easy. Theta was just going to be ranging from 0 to 2 pi. We were going to take these entrances and exits for all possible values of theta between 0 and 2 pi. This allows us now to finally set up this iterated integral. We have that the triple integral over this region E of x dv. We're going to have to provide quite a bit of space between these integrands. We know that our rho is going to be going from 0 to 1. We have our phi is ranging from pi over 4 to pi over 2. And finally, we have that our theta ranges from 0 to 2 pi. And lastly, we need to fill in everything in terms of our spherical coordinates. So our x is going to become rho sine phi cos theta. And our dv, again, is that complicated expression where we're going to end up having that we have that rho squared sine phi, and then a d rho, a d phi, and a d theta, making sure that this order here is consistent with the order on those limits of integration. A few remarks before we work through a few more examples. As we saw in that example, it's usually going to be easiest to set up rho first as your first variable of integration. Once you have rho, then you can choose whether or not to do theta first or phi first. I personally find using phi first a little bit easier. Spherical coordinates are going to be useful when your region is bounded by cones and spheres. Cylindrical coordinates when you have spheres and cylinders. When we have the cone, spherical coordinates is probably where we want to go. This is, again, generally because when we go from a surface like a cone into spherical coordinates, the equation ends up being pretty nice. And so those limits of integration in terms of phi end up being really friendly to work with. When we had a region of between two circles with double integrals, we like to use polar coordinates. Same thing can be said for dealing with a region between two spheres. It's probably a good idea to use spherical coordinates. In this case, we're dealing with a region between two spheres in the first octant. So to go ahead and draw this out, we have our sphere of radius 1. So it's going to look something like this. So here's my sphere of radius 1 in the first octant, giving it a little bit of dimension and depth so that we can see that it's actually a little sphere. And then we're also going to have the circle of radius, or sorry, sphere of radius 2, looking something like this. So trying to draw this one out as best we can. Again, just a rough sketch is all we need, but you do need a sketch. I can't fathom trying to do these without a picture. I wish you luck if you decide to not draw a picture. Draw a picture. So we're looking at the region between these two spheres as the region of integration. We're trying to determine the triple integral in terms of spherical coordinates where we have z dv. Okay, to set this up, again, I think that it is easiest to, and I'm going to give these a bit more space. Our z is going to be rho, and that's going to be cos of phi. And then the order, probably the best idea, as I mentioned before, writing it out as rho squared sine squared phi, and then doing d rho, d phi, d theta. Dealing with rho first is probably the easier way to go. Okay, so let's go ahead and work with our rho first. Okay, so where is rho going? So rho is always going to start on the inner sphere, and we're going to go out to the outside of the sphere. So again, here my rho is always going to be coming out from the origin. And so the first place that I hit is going to be rho equal to 1, and then exiting out at rho equal to 2. So we're going to go from rho equal to 1 to rho equal to 2. Once again, how do we get these equations? Well, we know that our circle of radius 1, so we have x squared plus y squared plus z squared equals 1 is equivalent to rho equal to 1. And same thing is going to be true for our inner circle. We have x squared plus, and I should say inner sphere, x squared plus y squared plus z squared equal to 4, which is going to be the same as rho equal to 2. Now that we have this, we have our different values of rho and our variation for rho. I'm going to draw a few more of these entrances and exits just so that we can see exactly what is going on here. We're taking these values of rho for any option of rho outside of the sphere. So I'll just draw a couple more so that this is really clear and hopefully easy to see. So here are our rhos, and now we need to go ahead and think about what is happening with our phi. So remember that phi is going to be the angle between the z-axis and the z-axis. So in this case, we're looking at what our angles could possibly be. I see that I could have a line like this, but because I'm restricted to the first octant, my phi is not going to pass pi over 2. So here we're going to get that our phi will range from 0 to pi over 2. And again, to draw that out here, we have our entrance and exit. We have an entrance and an exit here. I have my entrance and my exit. Always ranging from pi over 2 and 0. Last but not least, we need to figure out how our theta is ranging. And remember, theta is going to be the angle from the x-axis over. And here we can see that our theta is going to be ranging from we'll have 0 all the way to pi over 2. So again, 0 to pi over 2 for our thetas. This allows us to set up our limits of integration. So we have 0 to pi over 2 for our thetas. We have 0 to pi over 2 for our phi's. And last but not least, we have 1 to 2 for our rhos. And now we're left with this integral to evaluate. Pause the video, give this evaluation a try, and I'll be back with it done when you come back. For this integral, I chose to actually do something a little bit funky halfway between. So once I got down to evaluating in terms of d rho, we're integrating a rho cubed, so we're going to get a rho to the 4 over 4, and we're going to have a d rho d theta, which will end up, after a little bit of arithmetic, giving us 15 over 4 cos phi sine phi d phi d theta. While we could go ahead and integrate this way, I decided to switch the order of integration slightly and go ahead and, because here we don't have a terrible region to integrate over, we end up, can switch it to d theta d phi. And in doing that, we just have a simple constant to anti-differentiate. So that's going to leave us, after an evaluation, with 15 pi over 8 cos phi sine phi d phi. This requires a u substitution. I went ahead and chose that my u was going to be equal to sine of phi, so that my du was cos of phi d phi. And after that u substitution, we end up with 15 pi over 16 times sine squared of phi, evaluated from 0 to pi over 2, which in total gives me a value of 15 pi over 16 for the value of this triple integral over my region E. Once again, just to highlight in here to give it a bit more depth, we are looking at the region between these two spheres. So it is the region here. Hard to visualize, but trust me, with more practice and drawing, it'll get a little easier. For one last example, we're going to find the volume of the region between a cone and a sphere in a particular way. Here, we're going to use a triple integral where we would normally actually use a double integral. So with a double integral would be finding the volume over a region, whereas here we're finding the volume directly by using a triple integral. The triple integral that we're going to have to evaluate is going to be the volume integral, so over the region E that we're going to try to find, of 1 dv. So we're just going to be integrating over the function of 1, where our region is just the region we're wanting to find the volume of. To start things off, we need to go ahead and draw the region that we're trying to find the volume of. I encourage you to pause the video and try to draw this region on your own. I'll have the region drawn by the time you come back. Here is the region that we are trying to find the volume of. It's kind of like a weird shaped ice cream cone. And the next step that we need to go ahead and go through here is, once again, to get each of these equations into spherical coordinates. So once again, here we have that our first cone. So here we've got z equal to square root of x squared plus y squared. We actually went ahead and figured out the equation in spherical of this earlier. Remember that we ended up getting that this was equal to pi over 4. For the sphere, here we have that x squared plus y squared, plus we have a z minus 1 half squared equals 1 over 4. We'll have, if we simplify this slightly, we get x squared plus y squared. I guess this is technically expanding it. We'll get a minus z plus 1 over 4 equal to 1 over 4. So that we have that rho squared is going to have to be equal to rho sine, oops, sorry, rho cos of phi, because we have that our z is always going to be equal to rho cos of phi. Here we have rho squared, rho cos of phi, which will end up giving me that rho is equal to cos of phi. This gives me an equation of this particular sphere. Now notice that this sphere is centered at the coordinate z equal to 1/2. It has a radius of 1/2, and that's where the cone is intersecting with this sphere. Okay, we now have the equation of our cone and our sphere into spherical coordinates. So we're ready to go ahead and think about how our phi, theta, and rho are ranging. So to start off with our rho, because that seems to be where we always like to go first, remember rho is going to be where we are entering and exiting through this surface in all of these different directions. So here we're going to always be starting at the origin, and we're going to be exiting through the sphere. Entering through the origin, exiting through the sphere, entering and exiting, and so forth. We can even have these ones that are going through the back, like so. Our rho is always ranging from 0 out to the sphere, which is going to be cos of phi. We can do the same thing for our angle phi, which once again is going to be the angle from z to wherever we're stopping, the angle from the z-axis. And again, here we're going to have that this is where our phis are ranging. My phi can range this way, and around in these different directions. So once again, our phi is going to be ranging from 0 to when we hit the cone. So that's going to be so our cone, which is equal to pi over 4 in terms of phi. Remember, we've got that expression for phi right here. And lastly, we need to think about how our theta is going to be ranging. Theta is going to be where we are on our away from our x-axis. And once again, here we can see that we are going all the way around from 0 to 2 pi. And so this gives us a setup for our limits of integration. We can then rewrite this triple integral as an iterated integral in our variables. So we have that theta goes from 0 to 2 pi. We have that our phi is ranging from 0 to pi over 4. And lastly, we have that our rho is ranging from 0 to cos of phi. We're then left with 1 dv, or because we have our entire expression for dv, it's going to be rho squared sine phi d rho d phi and d theta. This is the volume. We now need to go ahead and evaluate this volume as a triple integral. So here we're integrating with respect to rho first. So we're going to have 0 to 2 pi. We'll have 0 to pi over 4. And integrating with respect to rho, we're going to get rho cubed over 3 sine of phi from 0 to pi over 4. And we'll have a d phi and a d theta. Evaluating this, we'll end up with 0 to 2 pi. We'll have 0 to pi over 4. And we'll end up just with a pi cubed over 3 times 4 cubed and a sine of phi, d theta. Lastly, we can get our integral 0 to 2 pi. We'll have this pi cubed over 4 times 4 cubed the antiderivative of sine phi in terms of phi is going to be negative cos of phi, and we're evaluating that from 0 to pi over 4. And then we'll have our d theta. From here, it's just a little bit more calculus to get to our final answer. Pause the video. I need to resize this to get a little bit more room, and then we will finish up. Picking up, now resized with some extra room here, we can see that we need to evaluate cos of phi from 0 to pi over 4. In doing that, we're going to get root 2 over 2 minus 1 and a d theta. And from here, we're basically done. We have the antiderivative in terms of our theta is going to be here. We're going to have 3 times 4 cubed. I'll have this root 2 over 2 minus 1 times theta from 0 to 2 pi. And then evaluating this, we end up with negative pi over 3, 3 times 4 cubed. We have root 2 over 2 minus 1 times a 2 pi as the final volume of this ice cream cone shaped region.